Welcome to Durable State of Persistence, where we cover storage-related topics in the container ecosystem. My name is Eric Forget, and this is Episode 3, Overview of Storage Provisioning in Kubernetes. The three patterns of storage provisioning that we'll cover today are volume provisioning, persistent volume provisioning, and dynamic persistent volume provisioning, or dynamic volume provisioning. We'll start with volume provisioning, and this is something that was demonstrated in the previous episode. We've got a single engineer here, and this engineer is in charge of the storage system, which is the left side of this diagram, as well as the Kubernetes cluster, represented by the right side of this diagram. This engineer needs to provision storage for their application. So first what they'll do is go to their storage system and allocate some storage. After the storage is allocated, the engineer will then go to Kubernetes and modify their pod or pod template to reference this new storage. This is what we call a direct volume reference. They're quick and easy to manage, especially if you're an IT generalist and you're working on both sides of our diagram here. The downside is that it's not very portable. It's tightly coupled to the particular cluster implementation, and there's no Kubernetes object tracking it. So if this engineer were to try to list the volumes using kube control, they wouldn't see anything. An alternative approach to volume provisioning is to use the Dory Flex Volume driver. The nice thing about the Dory Flex Volume driver in this case is that the engineer does not have to go and manually provision things on the storage system. The Flex Volume driver is responsible for that part of the workflow. In this case, the only step our engineer needs to take is to create a direct volume reference in their pod or pod template that references the Flex Volume driver. When the pod or deployment is instantiated, the storage will be created just in time using the Flex Volume driver. Like in the previous example, this is a direct volume reference and is therefore tightly coupled with the cluster implementation, and again, there's no Kubernetes object tracking it. In order to address some of the downsides of that direct volume reference methodology, Kubernetes introduced persistent volumes and persistent volume claims. What we'll talk about here is one of the patterns that we see where a storage admin pre-provisions a bunch of storage. And so as the story goes, our cluster admin sends a message to our storage admin and says, I need some storage. At that point, the storage admin creates a storage on the storage system and then communicates back to the cluster admin about the storage that they've allocated for the Kubernetes cluster. The cluster admin then has to create persistent volumes, and these persistent volume objects refer back to the storage that's been allocated. So these basically describe the units of storage that are available. When a developer or application owner then wants to leverage persistent storage, they'll create what's called a persistent volume claim. This persistent volume claim can be referenced by a pod or a pod template. So in this case, our developer or application admin is interested in getting 500 gig of stateful storage. When the cluster sees this new persistent volume claim has been created, it will look for the best match based on size. And the sizing logic is quite simple. As long as the persistent volume has greater than or equal the request size, the persistent volume will become bound to the persistent volume claim. That way nobody else can use it. And now this pod, which references this persistent volume claim, is now bound to this persistent volume that describes the storage that we've created on the storage system. This creates a nice portable abstraction, because now I can have my persistent volume claim simply a name, and if I move my pod or my deployment to a different Kubernetes cluster, This doesn't have to change very much. I simply have to create a persistent volume claim of the same name. So this level of abstraction gives us quite a bit of portability. You may have noticed that the only differentiating attribute amongst those storage objects was the size. Quite often we have applications that require high-speed storage, replication, encryption, different attributes based on different applications. And so in that case, we see this pattern emerge, which we call demand-based manual provisioning. In this case, the developer will tell the cluster admin, I need storage. Not just I need storage, but what are the specific attributes that I need for my particular application. The cluster admin then has to relay that information to the storage admin, who then creates the storage using that set of requirements. The storage admin then messages the cluster admin back and says, I've allocated the storage that you're looking for, here are the details. At that point, our cluster admin has to create a persistent volume that describes that storage, and then communicate back with our developer or app admin, telling them that their storage is ready. And usually what we do in this case is have the matching happen based on labels. So they'll provide some labels that could be used in the persistent volume claim object to make sure that our persistent volume claim is satisfied by the persistent volume that we've requested. Just like before, we get that level of abstraction here where my pod or pod template simply references the persistent volume claim. Once the cluster sees the persistent volume claim has been created, it uses the labels to match and then bind this persistent volume claim to this persistent volume, and now my application can save state. Similar to the volume provisioning workflow, we can automate some of this using the flex volume driver from Project Dory. In this case, we've replaced our storage admin with the flex volume driver. The workflow, again, starts the same. Our developer or app admin communicates their storage needs to the cluster admin. Cluster admin creates the persistent volume with the attributes that the dev or app admin are interested in, and then communicates back to them that same set of labels that the developer can use in their persistent volume claim. The developer creates their persistent volume claim and their pod or deployment. And just like before, our persistent volume claim gets bound to the persistent volume. What's different here is when this pod or deployment is instantiated, this storage will be allocated just in time by the flex volume driver. And this is what our end state looks like. So leveraging the flex volume driver from Dory, we've eliminated the need to talk to the storage administrator for each allocation of new storage. So persistent volume provisioning adds this layer of abstraction. The storage itself is no longer opaque with regard to the Kubernetes cluster itself. Next, we'll talk about dynamic persistent volume provisioning. Here we've replaced the flex volume driver with a provisioning controller, and this one in particular is the provisioning controller from Project Dory. The storage class is the cornerstone of dynamic persistent volume provisioning. The storage class can be thought of as a provisioning policy or even a template for creating volumes. The cluster admin creates a storage class for each level of service they want to offer their application admins and developers. The example is gold, silver, bronze, but these storage classes could be way more descriptive, could be replicated, non-replicated, replicated and encrypted. It could be prod, test, dev, really whatever the implementation requires. Once our cluster admin has set up a set of storage classes, our application admin or developers can reference those storage classes when they create their persistent volume claim. So if our developer or app admin was creating an application that required gold service storage, they'd create a persistent volume claim with a reference to a storage class called gold. The provisioning controller is watching the Kubernetes cluster for persistent volume claims that reference a storage class that the provisioning controller supports. So in this case, our persistent volume claim references our gold storage class, which this provisioning controller understands. Therefore, it's able to allocate new storage, and then within the cluster, it creates a persistent volume that describes this storage. And when it creates this, it creates it with a reference to the persistent volume claim. That way, we can ensure that the Kubernetes cluster is going to bind my persistent volume and my persistent volume claim. We can see here that the persistent volume and persistent volume claim are now bound. At this point, our app admin or developer can create a pod or a pod template that references that persistent volume claim, and now my application can start and take advantage of our stateful storage. This is what the end state looks like after we've dynamically provisioned storage. Two other things to mention with regard to dynamic volume provisioning. The first thing is that you can set one of your storage classes to be the default storage class. This means that any persistent volume claim that's created that doesn't directly reference a storage class will use that default class. The other thing, although we've been talking about provisioning, and I've called this the provisioning controller, dynamically provisioned volumes also come with a cleanup, an automatic cleanup. So by default, when this persistent volume is created, it will have a cleanup policy of delete. What that means is when this persistent volume claim is deleted and this becomes unbound and no longer needed, the provisioning controller, again, that's watching the Kubernetes cluster, will clean up the backing storage and then finally clean up the persistent volume as well. So that's dynamic volume provisioning. Obviously, we get the portability. Our volumes are no longer opaque. We get the automatic cleanup and creation, and really provides developers and app admins with a self-service method for creating storage. So that was our overview of storage provisioning in Kubernetes. I hope that this was interesting, if not entertaining. Thank you.